So my name is Ronald. For the people who don't speak Dutch, Luijten is very hard to pronounce, so just call me Ronald. But don't shorten my name for the non-Dutch. So don't call me Ron or Ronnie or anything like that. Neither myself nor my name like to be shortened. Okay. So Microserver, what is this? 4 years and a couple of months ago, somebody who actually is sitting with us in the audience gave me a Shiva plug, which was the start of my Microserver. And it actually looks like a little transformer that you plug into the wall to charge your iPhone or whatever. The wire comes out. The wire is in fact not power, it is gigabit Ethernet. And after some time, I was able to get an operating system, Linux, up and running on this part. And I had a web server on this, a virtual desktop, and I got this idea to measure the power. And then I noticed it was using 4.2 watts, even using an external rotating hard drive. And I said, gee, this is something that I want to understand, because this looks like a server, but it's very small, it doesn't use much power. And when we started to talk to the data center people about 5 years ago, they all told us about their worries about the energy consumption. And I said, this is something I want to understand. I want to understand how this impacts IBM's business. So lo and behold, we started working on microservers. For the first 2 years, it was kind of an activity that I did in my spare time, partly at home, partly when I had a few hours left at work. And then I discovered this SKA project about 10 years ago, and I said, this looks like a really interesting project. I want to be part of this. And then thanks to certain people at IBM, leveraging the great collaboration with ASTRON, we were then able to establish a project where we are doing technology roadmap development for ASTRON and SKA. And there's a couple of charts later on that. But the funding from the Dutch government then actually enabled us to start building stuff that you will see today. But first, let's start with a couple of definitions. So if you look at my title, it says the word microserver. And microserver is a term that is used quite a lot in industry, but not everybody means the same thing with this term. So let me give you Ronald's definition of microserver. My definition is, thou shalt integrate the entire server node motherboard into a single microchip, which is this thing, except DRAM, which is usually located here, no boot flash, which is somewhere on this board as well, and power conversion logic, because those three things is a really bad idea to integrate it into a high-performance logic process. So that's just a very pragmatic definition. And once you do that, you can actually compact a board of like, a foot by a foot into something that is 13 centimeters by 5.5 centimeters and have exactly the same function. And there's one thing that you have to notice, which is that when I say I want to make it small, it does not imply that I want to make this a low performance device. No. There are some people who mistakenly think that microserver means low performance. This is not what we're after at all. We're after very high performance, but in a small volume, and very energy efficient. So that's the first definition. The second definition is SKA. SKA, so let me ask you a question. I like to do things interactively. So who has not heard about SKA yet? Raise your hand. Okay, so there's a couple of fingers there, so I'll quickly go. So to me, the interesting aspect about SKA is that it A is trying to get the answer of why we're all sitting in this room. Okay, that's a little bit of a stretch. But what they're trying to find out is why the universe was created in the first place. And they do this by measuring the Big Bang, the real Big Bang. The project they're doing is completely comparable to what is happening in Geneva, in CERN, where they shoot protons at each other at near light speed, and they create mini Big Bangs. And so they're kind of simulating the real thing. The radio astronomers said, let's not simulate the real thing, let's look at the real thing. And so they measured the radio waves that were created at the time of the Big Bang. Now, the radio waves were created 13.7 billion years ago, which is a few days ago. And the radio waves have been traveling for 13.7 billion years. So how do you get those waves? It's very simple, right? All you do is you take a telescope and you look 13.7 billion light years into distance. So, simply done, right? So that's why you need, when you want to get those radio waves, an antenna that is very big, because your cell phone won't be able to get those radio waves. And the antenna is a square kilometer to make sure that you have enough energy collection from those radio waves and you can get those signals. And when you look at the Big Bang, then basically the theory says there was something that happened at time zero. And there's many steps. But I think for the SKA, one of the key science studies that they will do is kind of the time between 3 minutes after the Big Bang until 400,000 years after the Big Bang, which is known as the phase of reionization, which will explain a lot about how atoms were formed, how planets were formed, how stars were formed, etc. That will either confirm the theory that the physicists have put together, or it will cause people to have to think about how to adjust the theory when things don't match exactly what they expect. But this goes into one of the key questions that helps us understand everything about everything. So when I discovered that's what they're doing, I said, this is great. Now there's another thing which is comparable to what is happening in Geneva. SKA is a 10-year planning phase, a 10-year construction phase, and a 30-year use of an instrument that is a one-of-a-kind once they have built this, right? So this is a large undertaking. There's about 10,000 astronomers on the planet. They will use this single instrument globally, and we have to make sure that the measurements from this instrument are made available to all those people across the planet. And as Albert-Jan mentioned, this is a big data example. So the reason why IBM is in this project is because it helps IBM to also understand the big data challenges. So here's a couple of artist pictures on what the antenna might look like. So I hope I won't go into too many technical details. I'm a nerd, so I maybe say too many of those details. Just let me know if it's too much. So there's low frequency antennas, mid-frequency antennas, and high-frequency antennas. Basically, the radio waves from 70 megahertz to 10 gigahertz are being sampled. And the data that's generated out of this is amazing. It's why we call this big data on steroids. And there's about a total of 2 million antennas that collectively, at the end of the day, generate one signal. One end of the antenna is 3,000 kilometers away from the other end of the antenna, and at the end, we generate one signal. Think about that. There's a lot that has to happen to actually make this instrument work. That is a huge challenge. Why is this a challenge? Well, I won't go into detail of this picture. It just is there to show you that we do really complex things, so I hope you believe this now. But the point I'm making is that at the end of those antennas, we are sampling data which is a total of 14 exabytes per day. That is, an exabyte is 10 to the 18. 10 to the 18 is a really large number. I will stop with any comparisons to try and explain to you how large that is. After we do all of the processing, we keep about 1 petabyte a day, which is 14,000 times less. And we keep that every day. Now, 1 petabyte, I can explain a little bit better. So if you go to the media market and you want to store a petabyte per day, every day you buy 1,000 terabyte hard drives, you connect them up to the system, you fill them, and at the end of the day, you disconnect them, and the next day you do the same again. Think about how many drives you have after 1 year. Okay? So clearly, the MediaMarkt is not an option because they don't have those many drives. Right? Although I'm sure they're happy to sell them to you. Now, to show you the amount of processing that needs to be done, we have a graph here of what the top supercomputer performance is going to develop over the next so many years. Now, this is a projection, right? Right now we are at, say, 2014, around here. And when you extrapolate, and extrapolation is always dangerous, but when you extrapolate this, we get a machine that will have an exascale performance around 2020. That is about the time that SKA becomes available. And SKA doesn't need floating point performance, which is what supercomputers usually do, but still we need 2 orders of magnitude more performance than the exascale machine that will be available around the 2020 timeframe. And we have a power budget that is much less than the exascale guys. And the reason is very simple. The antenna, as Albert-Jan mentioned, is actually put into the desert in either Australia or South Africa for a very good reason. Because we don't want radio pollution. We're measuring radio waves which are very, very weak. And we don't want anybody there with cell phones or TVs or radios to do a pollution of the signal. So we put this antenna in the desert, right? It's also nice because the desert is free, so nobody complains about putting funny structures there. However, there's 2 immediate problems that we get when we put this in the desert. A, there's no power grid, and B, there's no internet, right? So how do we get the energy in, and how do we get the data out? That all has to be developed. And therefore, the power budget that people put on the project is quite low, right? The total should be under 10 megawatts. And this means that when you compare this to the technology that we expect to happen, that we need to have a factor of, depending on how you measure this, between, say, 180 and 1200 times of improvement. Now, a factor of 1000 times improvement is not something that you get by taking a deep mathematical study. You need to do everything everywhere in order to be able to force a breakthrough at multiple fronts, right? Typical breakthroughs for venture capitalists, they found when you can show a factor of 10 of improvement, they open their pockets. We need a factor of thousands. So it's 10 times 10 times 10. And therefore, we need multiple breakthroughs. So, this is how DOME came together. Now, I've worked at IBM for 30 years. I am sick and tired of acronyms. So I said, I don't want an acronym for this project. So we call this DOME for 2 reasons. Number 1, we have the Dutch working with the Swiss, although I'm both Swiss and Dutch myself at this point. And the dome is, of course, the covering of the building where an optical telescope is placed. But dome is also the name of the mountain, which is the tallest mountain that is entirely within the Swiss border. In German, it's actually spelled without the E, but for Dutch people, I don't want to show that spelling, because that mountain doesn't sound good. But I projected the Dome mountain, which is in the Wallis in Switzerland, so close to the Italian border. And it's 4,485 meters high, if I recall correctly, into this covering of the building. So if you remember anything, you remember the tallest Swiss mountain. Now, Dome, a couple of years ago, ASTRON was almost at the phase of completing LOFAR. LOFAR is driven completely by ASTRON, and LOFAR is kind of the entry level into SKA. So it is 1% of the complexity of SKA. So you can kind of think, oh, we just do 100 times LOFAR and we're done with SKA. Well, the reality is that the scaling is not linear. It is at least quadratic, if not more. So doing SKA is at least 10,000 times as hard as LOFAR. And so ASTRON came to us and said, we just completed LOFAR. With that, we have proven that the concept works. We've shown that we can build this. We actually are doing science with this, so we're now really excited to go ahead with trying to get SKA working, but we need your help, because there are so many problems and we don't think we can do this on our own. And so they approached IBM and we got the DOME project together. And I sat together with Mark de Vos, I think it was about 3 years ago, where we said, let's look at all of the projects that are of interest both to IBM and to ASTRON to attack the issues for SKA that are relevant both for ASTRON but also for IBM business. So we discussed about 20 projects, and at the end there were 7 that made it, and the 7 you see here. That's a holistic modeling analysis that we're doing to build better machines, including SKA, but also build better servers or data centers. Then we have a track on computing, on data transport, and on how to do storage. We think about how to store petabytes per day that 10,000 people around the planet want to access. We need to figure out how to do that, because that has never been done before. And in the computing track, we have microservers and accelerators, and microservers is what I will focus on for the rest of this talk. The point I'm making is that those 7 projects were selected because they are of strategic interest to both IBM and ASTRON, right? And then microservers. When then the DOME project allowed us to start building microservers, I said, okay, this is great, but what do I want to do? So I like to give myself tasks that are pretty hard. So I just gave myself the assignment that I want to build the world's highest density 64-bit microserver drawer on the planet. So I'm building the densest compute box that is at least 10 to 100 times more dense than anybody else on the planet. That is my goal. I don't know if I can reach it, but it's good to set yourself a hard goal. And of course, it should be useful for both SKA, so it is not decided that this microserver will be used for SKA. No, we're building this to see if we can use it for SKA and what we may want to change in order that it is useful for SKA, and the same for IBM's future business. So I call this a data center in a box, and we can do like business analysis, pre-product research with this. I want this to be very energy efficient, as energy is the #1 issue for data center operators in the future, and I want this to be very low cost. Right? So radio astronomers belong to a species of physicists, and physicists, like scientists, typically don't have large wallets. Right? So they want everything to be really inexpensive. Therefore, I want to use commodity components. Commodity basically says, you know, many people make these parts and they're really inexpensive. You can get them, you know, at Albert Heijn if you want. But not only for the components, I want to use hardware and software standards. So nothing proprietary, nothing that sounds like it's going to be expensive. And now, in order that IBM can build a value system of this, I want to add some value-add functions to this microserver, and I'll show you more in a minute. And then I need to ask you a question about the speed of light. So I just have to do this. So please raise your hand if you know how to increase the speed of light. I see no hands. Okay, well, I must say that, you know, I've asked this question over the past 2 years to probably the most intelligent 1% on the planet, and so far only one guy at EPFL raised his hand, and when I questioned him, he just raised it as a joke, so he also didn't have the solution. Now, there are 3 insights that are really key that drove me to say I want to do microservers. The #1 thing is that 98% of the energy, and remind, the energy was the #1 problem. 98% of the energy is in data centers used to move data from A to B. Send a bit from left to right. There's no value add in sending the bits, right? If you are a bank, the value add is you make an interest calculation on the mortgage that you have to pay. right? That's the value add for the bank. That's 2% of the energy bill. And we can only use electrical wires inside our server box because optics are way too expensive. And what we know is that the energy in a wire is proportional to the communication speed times the distance. And as you know, communication speeds have been going up, right? At your home, you see one from 10 megabit Ethernet to 100 to gigabit Ethernet. People are now doing 10, 40, 100, and even terabit Ethernet. The speed goes up. And since you don't have the patent to increase the speed of light, you give me only one option. I have to reduce distance, because otherwise the energy is going crazy, right? So reduce distance means I integrate the hell out of everything. And that's why microservers are a really good idea. And that's ultimately the motivation for me to do microservers. Now, when I talked to the IBM business people, and I said I would like to run DB2, which is one of the products that IBM makes, they basically said, Ronald, forget 32-bit. Now, when I started this project, you could get a plethora of 32-bit machines, but no, 64-bit. And you also, Ronald, have to run a real server class OS. You know, not some kind of an amateur thing like Debian or Ubuntu, which is great for, you know, when you want to do a student project, but not for real business. So I had 3 constraints. I want to have a microserver in my definition that you saw on the 3rd foil. I want to have 64-bit, and I want to have a real OS. So with that, 3 years ago, I started looking on the planet, and I basically discovered a part by Freescale, which is a company formerly part of Motorola in Austin, Texas, and they had a part which, by sheer coincidence, had a PowerPC architecture, ISA. And so I decided to go and build a microserver using their part. This is it. It's blown up, right? So this is 13 centimeter, 5.5 centimeter. It is inspired on a very inexpensive commodity called a memory DIMM that you probably have in your laptop, not your laptop, in your desktop to implement the memory of your computer system. We use the same connector because it's cheap, but we have redefined all the signals, and this then is our microserver. This is a complete business server, and I'm one of the very few people who can say, I've been carrying a server in my pocket for all day and you haven't even noticed. This is it. This is a working board, so I'm not going to pass this around. This is what actually is contained on this board, right? So we have the part from Freescale. In this case, we started with a P5020. We have 2 DRAM channels that has a total of 16 gigabytes on this board. We have 2 power conversion units for the 1 and 1.1 volt that is needed by this chip. A capability to boot this thing, and a thing that is called a PSOC. And in this PSOC, we have collapsed a huge amount of chips that you typically find on the motherboard to do the following functions. So we can do the power on and off of the chip that's here, and control the power of sequencing, right? Because there are at least 4 different power supplies, and you have to turn them on in a particular order, otherwise things don't work. Then we can do the U-boot configuration for the microserver, and U-boot is kind of the equivalent of the BIOS that you have in the Intel world. Then we can do the JTAG debug access of this thing, which is only for people in the lab, but you need parts to do that. Then serial port as Linux, when it gets awake, the first thing it does, it sends a message over good old RS-32. And then we do temperature monitoring and protection. So we measure the temperature on this chip, and if it gets too hot, we can shut it down that we don't get smoke. My manager, a long-time manager, told me once, you know, Ronald, do you know that all chips work on smoke? I said, I don't think so. He said, sure. You know, the moment the smoke comes out, they stop working. And then we have the management interface and control that allows us to turn on and remotely manage these boards, because when we put hundreds of them in a single rack unit, we have to be able to do that. We have two options for this, this board that we are currently developing. So a P5040, I won't go into details, but it's basically a 4-core machine at 2.2 gigahertz, a bunch of DRAM, but it's an older technology, 45 nanometer, and a total board TDP of about 55 watts. That's the thermal design power. So that's the amount of heat that is generated. We have a much newer version called the T4240 from Freescale, which is 1.8 gigahertz per core, but it is 12 cores, but times 2 threads, so we have 24 real threads. Think about that in that board. And it's 28 nanometers, so much newer technology, and therefore, even with more compute, with the newer technology, we are still at a wattage of about 60 watts. But across this connector, we now get 2 times a hard drive interface called the SATA, and 4 times 10 gigabit Ethernet. Now, you're already challenged to find a desktop that has 1 times 10 gigabit Ethernet on the back, right? We get 4 of them across this connector. And we put all of that in this form factor, right? So the T4240, we have 4 times 10 gigabit Ethernet, 2 hard drives interfaces on this, and 48 gigabytes of DRAM on a board of this size. This has not been shown by anybody, as far as I know. Then, this is just to impress you, to say we do really difficult things, right? I'm not going to go into any details, but you see, many colored blocks of different kinds and sorts, and it just says, Freescale was able to put everything that you ever needed for a server into a single chip. That's all there will be a quiz, this afternoon at 5:15 when you have a drink, and I will ask you what is this block. Now, hot water cooling. This is another favorite topic of mine. Many people say, how can you cool with hot water? When I'm hot, after a hot summer's day, I want to take a cold shower, not a hot shower. So the answer is, well, there's hot and hotter, right? Chips work at typically a junction temperature of 85 C, 85 degrees centigrade. And the water that we use to cool this is at 50 to 55 C. That is still 30 degrees difference, and I can cool with 30 degrees difference. And then you say, well, why do you go through the trouble of having hot water? And the answer is, well, I can sell hot water as a commodity, right? Because the 55 degree hot water I can then use to actually feed into a central heating system on the home, so I can get free computing, right? So in Switzerland, what happens is that most houses actually have a oil-based central heating system, and what you do is you take oil, which is nothing but diesel, and you burn that to create heat, and you heat your house. So what I say is I don't burn the oil, I put this into an electricity generator in the form of diesel, I generate electricity, with that I run my microserver system, and the heat I then use to heat the house. So I get free computing. It's a good idea, right? I don't pay for the electricity because I already was generating this in the first place. Now, this is not a wild idea, this has been shown. So our lab, the IBM Research Lab, has been instrumental in building a system that is called SuperMUC. So MUC is the airport code of Munich, that's why it's called this way. And we have built a system at scale, so here you see a picture. So that's many, many racks, a whole machine room full of hot water cooled compute nodes that were the number 4 entry on the top 500 list 2 years ago. I think now it's like number 14 or so. And now hot water cooling has a couple of interesting advantages. You actually need 40% less energy to cool the system than if you were to use air. Now, most systems today are air cooled. And as I said, you can then reuse this waste heat because you can sell the hot water as a commodity. The fact that you use water, water has a heat carrying capacity that is 3,000 times higher than that of air. So I can space things much denser together than if I do air cooled. And so I can get high density. I'll forget about those things. So all I want to say is it has been shown. So how do we do this with our microserver? So with our microserver, we take the board that I just have shown to you, and on top of that we put a copper plate after we remove the heat spreader that is part of the chip from Freescale. And we remove the heat spreader so the chip is directly exposed, and we put the copper plate on top of that. And this is the way it works. So here I have my copper plate. This is solid copper, you would think. And then this is the chip. And then we have a thermal interface directly of the copper to the chip. We put this together, and now I can take the 60 watts of heat that is generated by this chip out of this chip. And then I can place the total thickness of this board with the plate is now 7.6 millimeters, and I can space those boards 7.6 millimeters apart in a rack unit. Now I said solid copper, I lied. It is in fact not solid copper. It is a laminated copper plate. And what you see is that we have ground and a power and a ground layer that are connected with nails or rivets to the power supply levels on the board. So when I was in university, I still remember a few things about that. They taught me, as an electrical engineer, that copper can carry electrons really well. So we use the copper plates to carry the energy in as well as the energy out. So heat in or electrons in and phonons out. This is an innovation that we did. It's patented. And then we do the conversion of the 12 volts that is transported through the plates in a power conversion unit here and here to get to the 1 volt that you need for the CPU. So this is the main power delivery to the board. There's other powers that are needed which go across the DIP connector, which is needed for the dynamic memory, the DRAM. So once we do that, and this is a plan, we have not built this yet, but we intend to have this operational by the end of the first quarter of 2015. We will have a rack unit, so 19-inch rack unit, where we put 128 of these compute nodes into this unit. Here is a water pipe that carries in 50-degree water. Here the 55-degree water comes out. There's pipes that run this way. And here you see fingers. And these fingers go across the edge of this copper plate to deliver the electricity and to take the heat out. So they're electrically as well as thermally coupled. And then there's boards of other kinds, so we'll go more detail in a minute. And this then allows us to put 128 compute node boards into this 2U rack unit, which is an equivalent of 3,000 real threads and 6 terabytes of DRAM. I call this a data center in a box. This is a unit, a rack unit, which is this high, it's this wide, and probably will be this deep. This is unprecedented. Nobody has shown this amount of density before. We're doing this as a research project. Now, software. You can't build a compute system with hardware alone, right? So you need software. And basically, Freescale builds these parts for what is known as the embedded market. So that's not general purpose compute. They build this for mobile cell base station towers. They build this for avionics, for probably many applications I don't know about, but not for general purpose compute. So I worked with Freescale 2 years ago to show that we can run a real 64-bit OS on this thing. So after we figured out how to do this, it took us a couple of months, I was able to run all of this software. So the operating system Fedora, IBM DB2, Hadoop, and a bunch of other things that I don't want to bore you with. Now, what is the status? Today, we basically have the first version of the node boards that I just showed you working. So we have U-boots, the BIOS, the hard drive, we have booted Linux in 64-bit mode. We just received the new board for the 4240, and I will start bringing up in the lab next week. We have a power module working, so this is the separate power module I mentioned earlier that is generating the power for the DRAM, separate of the board. It can actually generate 150 amps at 2.5 volts. So that's quite a lot. And we are starting the bring up of a multi-node carrier board. So this is a small section of this large 2U unit with a 128. Here we can put 8 boards on in various configurations. And this will be our mechanical test of the water cooling, as well as doing the clustering and bring up software. I recently got a Silicon version 2 development system from Freescale that I got installed. And today is in fact the announcement that we say we make the P5040 available to everybody who is part of the Dome user community. And that's what this event is about today. Here you see a picture of a thermal test vehicle. This is a board that is not a functional CPU. We have a chip here that can generate heat, and we can measure the temperature on this chip at various places to be able to validate the whole thermal packaging. Right? We take this stuff seriously, and we build various test vehicles. So on the 3rd of April, so recently was the first day we got actually Linux up and running on this system in the lab. And so here you see a lab bring-up baseboard that can connect only one compute node. Since we don't have water cooling for the first bring-up, we have a fan to cool the chip. Here you see instead of the copper plate, the wires that go to the power supply in the back to power up this thing. And I would like to show you a short video that actually shows that we booted this. Where is it? This video went. Here it comes. So you see the power supply, you see the fan turning, Dome logo. You see the screen of my laptop, and we are just starting Linux. So here you see the Linux kernel booting. And here we type a command that shows you the Linux kernel version. So you see we actually run a fairly modern kernel, 3.8.13 kernel. So that's this part. Now, what I would like to do next is a first. I have never at a presentation to try and do a live demo. So let me see if it works on the current slide. So, as I mentioned, we have DB2 running on our microserver. And what I would like to do now is to actually show a live demo where we run the real DB2 engine on the Freescale microserver. I don't have the microserver with me, it is in our lab. But thanks to the internet, what I do is I connect from my laptop, which is here, through the internet to the microserver, which is still in Zurich. And the demo basically says we take a pre-packaged, what they call a basket of transactions that simulates how people buy tickets for airfare. So we call this a simulation of an airline reservation transaction system, but we run this simulation of those transactions against the real DB2 server that runs on the Freescale part. So we actually have the server running on the 4240. Actually, I accessed it as a remote site that is called Swiss Dutch. I mentioned that I'm Swiss and Dutch, that's why his website is called that way. And this is what I said. So now let me see if we can make this all work. So as I said, this is the first time for me at a presentation. So here I use a program that is called VNC that accesses the virtual desktop on the microserver, which sits in Zurich. So it works. Oh, look at that. And now I need to see what I need. Okay, so now I will actually start the DB2 program. And in order to do that, I have to say start DB2 and enter. So there I go. This takes usually about 10 seconds. And so while this is going on, yes, it actually says successfully. I'm happy to see that. Then I have to change to a different directory. I'm really bad at typing in front of the audience, so I recall the commands here. Then I go to a different directory, and then I start the program that allows me to play to this WMD is the workload manager daemon that allows me to play this stuff. So this is all been running on the microserver remotely in Zurich, access to the internet. Isn't the internet wonderful? So then I go to a regular browser. Here it is. And through the browser, I then access the Technology Explorer front end, which is the engine that allows me to exercise this basket of transactions. And the way I do this, I say first I want to connect. I say connect. I will not show you what password this is. And the web front end is actually running locally on my laptop here. And then once this happens, then I say tool, do the workload multi-user driver. Then I hit this screen, and I go to the workload test. And lo and behold, I say run. And now I am running this pre-packaged basket of transactions, and I can actually modify the users. Now what you see happening here is that I get an update of the screen every second, and you see that this is the total transactions, this is writes and reads. Now this stays the same unless I do something to the users. So I say I want, so these users are really fast. So typical users are not that fast. Nobody thinks in 200 milliseconds. So I'm going to make them think in 5 seconds. So now they think in 5 seconds, and you see that the screen below changes. And here's only 10 clients. Now, how many people do you think are concurrently buying tickets at the airline? Probably more. So I'm going to make 500 clients. And then these clients are all doing things sequentially, which never happens. So I make them random. Okay. So I'm a very happy person at this point because this is working. So here you see now that writes and reads are exchanging and the transactions go up and down. At some point in time they go to 0. Should be at least. Perhaps they need to think longer. Let's make them think longer. So 10 seconds. Yeah, now it goes down to 0. Now we're all thinking. So that is the live demo of DB2 on a microserver. That has never been shown before. Next, from current slide. Now, I didn't do this work all on my own, as you can imagine. I may have been the visionary, I may have been the driver to get this project going, funded, and stuff like that. But it's a global project. There are people from many companies, not just IBM, so there's Freescale there. The company that built this in this room, I hope I actually put it on there. People from ASTRON, people from IBM in the US. Oh, here you see the transfer in the Netherlands. So many people, not all of them full-time, are working on this. Now this concludes the first part of my talk. I go to the second part of my talk, which is the potential microserver application areas, right? So the goal of this project was to evaluate how microservers might be used for SKA, that remains to be seen, and to evaluate how microservers may be used for IBM's business. That remains to be seen, right? However, given where we are today, we are completely convinced that there's an absolute great opportunity for microservers to go in those two areas I just mentioned, but also into other areas, because I think what we have is absolutely unique. And remember, this was done with the help of Dutch government funding, and so Dutch government or Dutch companies should take this technology and exploit it for growing business. So we will help you to start thinking about how you may use this. So the way you look at this, right, and once more, it's really small. If you compare this to a cell phone, it's the same size as a cell phone. Right? I'll give you back this low performance piece of computer. Still happy I didn't steal it, right? So we have very low cost of full 64-bit computing and networking. Right? There's lots of Ethernet networking on this. It is fully standards-based, right? There's no surprises. There are open standards. You can buy various stuff that fits with this. No dorky stuff. It is ultra dense, right? With water cooling, the density you get with this is unprecedented. And nobody says you have to use water cooling. If you want to use one, you can use air cooling and still have a pretty impressive density. Denser than what you get in your typical desktop at your house. And although it is very low cost, it is very high performance and it runs as standard Linux. So what more do you want, right? I offer you something which is virtually free. You have to pay a little bit of pocket money for this, but it's virtually free. So what can you do with it? So the team sat down earlier this week and we brainstormed. I don't know how many ingredients were needed in this brainstorming session, but we brainstormed about certain things you could do with this. So here's the first one. An intelligent refrigerator that actually figures out what is on the inside, figures out what your habits are, on what you need when, at what day, and make sure that your fridge is always filled with the stuff that you need, so you don't have to worry about this yourself anymore. There's enough compute power to be able to do that. That's example number one. Example two, smart TV. Same thing, except the smart TV doesn't figure out what you want to eat, but figure out what you want to watch. Example number three is probably more interesting, a self-driving car. Now, the compute power that you need for a self-driving car is pretty high. And if you look at the videos from various companies that are doing this, they say, yeah, currently when you open the trunk, there's our computer and you see the huge box, and we can put it onto this thing, right? So I think any company that is doing kind of this type of work should naturally be interested in this technology. Now, when you think about cars, you can think about something else, which is my passion, but I was told I shouldn't mention this, which is avionics, right? Flying. And
So you mentioned.
And I know that Freescale is actually marketing these parts to go into avionics, but I think our packaging is much more than typical avionics system that I've seen using the parts. And then the last example is where I challenge you to figure out what that might be, right? So I say, use your own imagination to figure out where you may want to use this, right? Because the brainstorming that we did was limited by nerds who were doing radio astronomy and IBM data centers. So with that, I don't know if the intent was to have questions at this point in time, or would you like to do this later?
We'll take some questions now. Ronald, thanks very much for your explaining a bit crux about microservers and give some hint what we can use it for. So are there any questions for Ronald?
There's one in the back.
Yes, please.
Do we send microphones around? Because there's a streaming event.
If you could pass this around, please.
I was wondering, in your live demo, where you use DB2 as the database on the microserver, Did that use the internal memory, or is there also, I mean, where is the storage going? Is that also in the microservers?
Okay, so as I mentioned, the microserver has a SATA connection. So the root file system is located in the SATA drive, which is of course not in the same size, but it is right next to the microserver. And so basically when you boot Linux, it loads the entire environment from the root file system into memory and starts running. And when I execute the db2 command, it goes to hard drive to load the appropriate executable and libraries. And so that is a regular compute system. We are, I don't have pictures of this yet, but we are in the process of still building what we call a single compute node experience platform, and that will be basically twice the size of this. So it's a board that will be the total size of this, and half of the board is actually this thing actually laid down on the board. And then right here we have all of the power supplies that are needed in addition to the one that's internal to run this board. And it has a 12-volt connector, it has a Ethernet connector, and as part of this board we have an mSATA drive that contains the entire root file system. So with that you get a single user capability to play with a single node connected to Ethernet. Do we have other questions? There.
Please pause it. And let's quick one.
Well, it's very impressive. And now that you've shown the way, how soon will this be superseded with something that's 10 times as small?
Well, I guess that depends on a few things. So you'll probably notice that I rely on parts from Freescale to build this, right? Now, building a chip of this type of complexity is in fact a very expensive undertaking. You need a huge team, several hundred engineers, and you need very deep pockets to be able to run a chip through the fab. So part of the answer is, if somebody were to give me $75 million, I would build my own SoC that would allow me to do exactly what you say. In order to get a factor of 10 of density, what we need to do is to leverage 3D packaging. And there are capabilities to do that. There is a company called Micron that is building HMC, or Hybrid Memory Cube, which is 3D packaged memories. I'll make that clear. No, I don't have a picture, but I can show it here. So on the back, it's kind of hard to see in this light. Perhaps I put it here. So you see that the memory is basically 9 chips. Right? But these boards is a two-dimensional world. It's 2 dimensions. It's not 3. Because I have a planar, I have a chip on here, and this chip talks to the memory that sits here, it talks to the memory that sits here, it talks to the Ethernet that sits here. In order to get higher density, we need to leverage 3D packaging. Now, the 3D memory chips exist, but they have a different interface. The interface is not supported on compute chips at this point. And if you say, I want a factor of 10 more density, I know exactly how to do this, but I need some pocket money to be able to get this going. Now, other people may be more successful at obtaining that pocket money and implementing that idea, I don't know. But what I would do is I would, you see there's a chip carrier here and there's lots of empty space. What I would do is I would take this chip, put it directly on the carrier, make the carrier the size of this board, then I don't need the board anymore, because that is then the board itself. And then I would, instead of 9 chips next to each other, I would put 2 chips that are the memory, or the 2 memory channels. And then I can put, let's say, 4, I can put 3 on this side, and I can put 3 on this side. That's 9 times denser. Is that close enough to 10?
Okay.
So we know how to do it, but it takes a little bit of investment to get there. Yes, please. There's one question in the back.
Yes, I can do it without microphone. I think.
No, because the streaming people will not hear you.
Thank you. You say it's low cost, and of course cost depends on many parameters, but can you give some clue on what is low?
So the bill of materials cost for a single node that I've just shown to you in quantities of 1 is about $500 in bill of material cost. So that's the components that you need, including the card, to build this. So when you go to volume production, you can guess from experience what it will do to the ultimate price of this. As you say, it depends on volume, right? I do have to hasten, going back to the previous question, 3D packaging will then become a lot more expensive, right? Because the components may be commodity, but the packaging of 3D at this point of time in 2014 is very, very expensive. So that is probably the reason why companies have not really embarked upon this. I think I saw one more question up front. Yes.
Yes, one more question. Alexander?
Alexander Brink. Well, feel very honored to be sharing Dome. It's being very impressed, Ronald. Thank you for your presentation.
Thank you.
And of course, the questions we all have is simple things. I recently was here at Cat 7, was the picture that you have here. And the first question that comes up is, we are in an over amount of sun area, an area with an overload of sun, and there is no solar panel. Right? That's the first thing. You know, you've got if you look at Meerkat, which they're building there, and you look at the power production units, they have that IPPs. It is massive. I mean, you're really still jarred for another half hour when you leave the room. So the microserver is all about sustainable computing in the end.
Correct.
And the point is that it's also sustainable computing and sustainable society are linked very close to each other. I mean, the increase of carbon oxygen is tremendous, especially with data centers in the US. I recently heard by Professor Tom Balstra, the director of Zernick Institute for Advanced Materials, that 2% of world oil consumption is consumed in Saudi Arabia, 25 million people, for cooling. That I wouldn't have believed it if it weren't Professor Tom Balstra, so it was probably the only reason to believe that at all, otherwise we think it could not have been true. So the point is, this is something I think we really need, and what would be a feasible process to get this really up to the market and also understood by society at large? It's a bit a long question, but I think the context is important.
Well, I think the first thing is, so if I let me reinterpret your question a little bit and ask the question in the following way. How can we use a reusable energy source to power up our data centers, including microservers, if that is what we choose to do? So solar panels is kind of a technology where you immediately, especially in the desert, say this is the way to go. The problem with solar panels as they are today is that they're actually very inefficient at converting the energy from the sun into electricity, right? You get, under laboratory conditions, you can get like close to 40%, but those are unaffordable. If you take a look at solar cells that you can buy, economically, the conversion is less than 20%. And so that means 80% of the energy from the sun you actually throw away, but you use all of the area. So perhaps it's not the way to go. Now, if you look at the way they do conversion of solar energy in those new institutions like in Spain with mirrors, where they take the energy from the sun and use mirrors to project this into what I would call a tea kettle at large, where they then convert water into steam and drive a turbine. This is a much more efficient way to do that, which is probably also a lot cheaper, because producing a solar cell is actually kind of a nasty process, right? So there's lots of materials and bad chemicals that come out of that. And When I was in the desert, I noticed something else. There's a lot of wind. And wind is something that you can convert much more efficiently into energy than sun. So my favorite way to power SKA in the desert would actually to be, a real Dutchman and put windmills in.
You're then getting it through into society.
I don't know the answer to that question. I think it's a very important question. But here I would just say I'm just a dumb nerd scientist who don't know how to deal with that.
Okay, thanks.
That was one point. Shall we take one last question?
Yes, one last question.
One technical question, but when you embarked, you said that you want to have a 64-bit chip, and you found one with the Freescale, which is a PowerPC architecture.
Yeah, it's 64 bits. The one I
64
showed
bits.
with the 64 bits.
It seems that the world is getting bigger on ARM. How do you see this microserver? You think you still have a PowerPC 5 years from now?
So IBM is investing very big in the Open Power consortium, 64-bit power. Right, we have actually released the Power 8 core as an open contribution to anybody who would like to use it with an Open Power. I think time will tell whether in 5 years Power is there to stand there next to ARM, right? So we did a study 4 years ago, and it's in one of the papers here, in fact. So I forgot to mention, we do not just build hardware, we also do scientific publications at peer-reviewed conferences, right? Those are the papers that we have written on the topic that is relevant. But this one is the paper that will give you the answer on your question. And I'll summarize it for you. Basically, what we did 4 years ago, we took 45 nanometer CMOS implementations of x86, of PowerPC, and ARM, all 32-bit. We compiled the same Linux kernel to them, we ran the same benchmarks on them, and we measured the energy that was needed to generate the answer. And the conclusion is, energy per answer is the same across all 3 ISAs. That leads to the insight, the ISA does not matter. And to me, what matters is, what is the cost of getting the answer in terms of the energy needed and in terms of the dollars needed to get the answer. And whether this runs best in terms of total cost on ARM or PowerPC or x86, we will let the world decide. To me, I will take the platform that is best to serve the purpose. And time will tell which one will survive. Or which ones will survive. So I think with this, it's the end of the live streaming. So I thank the world for attending, and we'll continue in private.
Yes, may I add to this, the audience in the world listening in. We have a website, www.dome-exascale.nl. Also, you can reach us via email. It's info@dome-exascale.nl. So if you want to have more information or contact or any questions, please contact us. And thanks very much for your attention for this event this afternoon. Thanks. Okay, so after this excellent introduction by Ronald, now it's time for the first of the 3 partners.